Hello everybody. So let's take a look at this problem that you see here, which is right off the assignment. And it is, like I said, right off the assignment, and you can see it here. So I'm not going to read much about what's there. I'm just going to, you could read this through pausing the video if you wanted to, or maybe you've seen this problem on the assignment already, but I'll just tell you my take on it, okay? So what it says here is that we've got a sphere and an intersecting plane. And if you look at the region above where the plane intersects the sphere, we get this cap called a spherical cap, and it's got a radius and a height to it, like you see in the picture. And then I have this formula that tells me the volume of that region above the plane right there. Okay, so here's the idea that we have. I get this equation, which tells me if I know the radius and the height of this region that you see there, I can calculate the volume through this. Okay, I don't really like the way this is written. I know that at some point I'm going to find a derivative, and I think it might be a little better if I distributed this through 3r minus h. So I get like that, and I'm going to go ahead and use this form. You could do it different if you wanted to. That's just what I'm going to do. Additionally, I've been told that, let's say that the volume of this is pi. So that v there in this equation is not a variable. It's a constant, and I know that it's pi. So I'll take what I've reduced it to, and I'll put pi for the volume. And then I notice that that's a real convenient number for the volume, because I could divide both sides of this equation by pi, and I reduce it to this. 1 h squared r minus 1/3 h squared. Okay, all right, so that is an implicit function where r is a function of h, and I'll explain a little bit more about that in a minute. It relates the height and the radius of the cap. So like, you know, if the volume of this cap there is pi, then you tell me the radius, I can tell you the height, or vice versa. You tell me the height, I can tell you the radius. That's what this does right there. Now, why do I say it's an implicit function? R is a function of h. Well, it's because of this, okay? I'm being asked to find this derivative, the derivative of r with respect to h. Or you could say the instantaneous rate of change of the radius with respect to the height, okay? Now, that derivative being the subject of this question implies that the radius is a function of the height, okay? Meaning that the height is the independent variable and the radius is the dependent variable. All right, that's what we mean. So in that equation, all right? Now, if you want an analogy, okay, maybe ordinarily we use y and x as our variables in our functions. So like ordinarily we might find dy over dx, the derivative of y with respect to x, implying that there's a function where y is a function of x. So if you wanted to, just by analogy here, if you don't like r and h and having to think about which variables which, if you just don't like that, then it's an analogy to this and that. So it would be like, if you wanted, finding dy over dx of this, where you see x and y like so, and of course with the volume being pi. All right, so that may help you think about it and have a better analogy to the way that our other problems have been. Okay, all right, now here goes. I want, as I mentioned, dr over dh, the derivative of r with respect to h. That's in Leibniz notation. You could also call that r prime if you preferred that notation. Okay, the technique there is implicit differentiation. I don't see that this equation explicitly tells me r from h. This equation is not arranged that if I plug in the h, I get the r. So the variables are all mixed up there. So the technique of finding the derivative is implicit differentiation. So step one would be to take the derivative of all terms on both sides of this, which with whatever rule applies with respect to h. So I'm going to look at it like h is the independent variable, that the h is like ordinarily how I treat x, and so on. And the r is like ordinarily how I treat y. That's what this step here with my red pen means, taking the derivative with respect to h. That would look like this. for the derivative of 1. 1's a constant, so I get 0. H squared times r, well, that's a product of two variables, okay, a product of two functions, you could say. So I need to use the product rule, so derivative of h squared is 2h times r, plus the derivative of r is r prime, then times h squared. Why do I say the derivative of r is r prime? Well, because in this example, r is behaving like y ordinarily would for us, and h is behaving like x ordinarily would for us. So there's the product rule with that consideration. And then I get minus 1/3, and then the derivative of h third power is 3h squared. Do a little simplifying and I get this. Okay, so there's the conclusion of step 1. Okay, what's step 2? Well, I am looking for r prime. I'm looking for that derivative, and I see that it makes an appearance in my equation in step 1. So I hope it makes sense to you that for step 2, I'll just solve for it. Sorry, I'll know what it is at that point. So I do a little algebra to rearrange this equation, ultimately solve for r prime, and if you want to call it dr over dh, you can. It's h minus 2r over h. It involves, like I said, some algebra, some factoring, some canceling, but you'll get it down to there. All right? Okay, so that takes care of this. Find dr over dh, the derivative of r with respect to h, under the assumption that the volume is pi. Okay. All right, now the next part says, what is the derivative when r is 7 and h is 5? Well, that part should be easy. I'll plug those in there appropriately. R is 7 and h is 5. I get negative 9/5 if you want. Okay. And I guess you could say 1.8 negative if you want to. Okay. Now, I want to ask you something, though. Like, it's easy to plug numbers into formulas, but here's what I think would be more important. Does it make sense that that derivative is negative? Like, say, before we even did this question, could you or should you have expected that that derivative be negative? So think about it like this. The derivative tells me how the radius and the height of this cap change together if the volume is fixed at pi. So I ask you, if the height got bigger, but the volume had to be kept the same, what would the radius have to do? It would have to get smaller. So what I'm seeing here is, in order to hold the volume constant, if the height got bigger, the radius would have to get smaller. Okay? They can't both get bigger and keep the volume the same. So I should have known from that alone that this derivative would end up being a negative number. All right. Okay. Now, so if you want more details on it, we can look at it like this. I'm keeping the volume. This is all under the assumption that the volume's constant. It's held fixed at pi. It's confined to be pi. It's going to be held constant, however you want to see it. So if I can reduce this to negative 1.8, it says if the height increases by 1 unit, the radius would have to shrink or decrease by 1.8 units to keep the volume at pi, to keep the volume the same. There's some compensation that's got to happen. Okay, so now it's like those proportional. That's if r is 7 and h is 5, but still I'm not at all surprised about that negative. H goes up by 1 unit, r has to go down by, almost twice as much. Okay, so that's how we can understand that derivative. That's how we can understand the number. And I hope the situation appeals to you, especially with the drawing, that you can grasp that. I hope you see my analogy that although the variables are different, I can treat it like y and x. It doesn't change the nature of the procedure. Just I have different symbols, r and h, that's all. And lastly, I would sure like it that even if you didn't expect this from the beginning, you now see why we should have expected the derivative to be negative.